568 teams submitted viable solution papers in the 2011 Moody's MegaMath Challenge. Of those, 37 were distinguished with finalist or honorable mention prizes, and the top 6 teams were invited to Manhattan to present their papers to a panel of professional mathematician judges.
Good afternoon, everyone. We're Team 121 from Eastside High School, Gainesville, Florida. Today, we're pleased to be here and present to you our solution to this year's problem, Colorado River water. A dry topic? I droughted.
I sub N represents the percentage of the inflow rate, A represents the average inflow rate, and O sub N represents the outflow rate. Our group is kind of like a specialist team, so we have some people like some strengths and other people's weaknesses, and so we kind of all mash together and use our strengths to the best of our ability.
This table shows the probabilities of the inflow having to change. And when the inflow changes, this has a direct impact on the lower basin receiving water. When we first approached the problem, we had a lot of research, but I mean, we had all this information, and then it's kind of like, what do you do with this? Well, you have to figure out which parts matter and be really selective in choosing which ones you want to implement in your paper.
Well, I was interested in this one because it was applied mathematics, which I find relatively more interesting than theoretical mathematics, mostly because it has a real-world solution and can actually have broad impacts unrelated to the actual field of mathematics.
It offers a chance to really apply mathematics. You almost never get a chance to take the math that you learned in school and then put it on paper, but for something much bigger, something like a dam.
It is important to note that the only 2 variables are the flow and the effective head, being the difference in elevation between the inflow and the outflow.
So I determined that a legislation mandated 6% increase just to 85% efficiency in sprinkler systems would have saved 153,000 acre-feet of water in 2008 alone.
This year we were expecting like a big global issue, and it turns out to be a dam in Colorado.
For the challenge day, in the first hour, we all worked together doing a bit of general research, and afterwards we branched off based on our strengths. So those who were good with politics worked on the last section that dealt primarily with politics. Those who were good with economics worked on more of the economic section, and the rest of us developed the mathematical modeling, the physics behind it, and etc.
We met up a few times, we looked at the past problems, and we did a few mock Moody's problems to improve our modeling, improve our teamwork during the actual problem.
Large sums of capital are needed to commercialize alternative energy or to install desalination plants, and therefore a trade-off analysis will be necessary to determine the feasibility of these options.
For the Moody's MegaMath Challenge, there's a lot of research involved, and there's also a lot of writing. And you also get to apply your mathematical modeling to a real-life situation, which I find really interesting.
Over 29 million people and 4.5 million acres of land rely on water from the river each day.
We collected what the effect would be on power generation, how much water there would be in the lake, what was the real importance of the lake, and in the end we even came up with a figure that the entire river system is worth about $8 billion of the GDP.
The data was really sparse for the economies of different states because each state has different ways of keeping their data, so it was a little difficult to find all of that.
When somebody realizes I might not be able to wash my hands if somebody doesn't take care of this river, that makes them vividly realize that math is something that affects their daily life.
We're thrilled to be here today to present to you our solution to the 2011 Moody's MegaMath Challenge, Colorado River water, good to the last acre foot. With our solution, not enough dammed water.
The evaporation rate varied too widely in order to be held constant, and so we decided to create a model for it. You have to be comfortable trying something that's very different from what you've done before. You have to think outside the box really and work well and communicate well what you're thinking so that you can use your team for your advantage, which I think we did.
I think one of the great things about this competition is you get a problem and you look at it and it might not have been something you thought would have applied to math. And this year is about Lake Powell and the different economic impacts, and it really teaches you that anything can be quantified.
Municipal and industrial uses account for 22% of water's total value in the lower basin area. It has very grave consequences, however, on the future of the lower basin as it greatly impacts economic growth.
We just practiced a lot, went through what we wanted to say, made sure we were hiding the important things in the allotted amount of time, and just rehearsed more and more.
The
there was an opposite or inverse relationship between price and quantity for shift, and there was a direct relationship between price and quantity for movement along the curve.
Coming to this building, it's awesome. This Moody's Corporation, just the feel of it, it's really amazing.
I think sometimes when you open a textbook in math, you don't really think about how it applies to the real world, but this forces you to look at connections.
We decided to find a correlation between the two, like volumes. We used a linear regression model, which yielded an equation shown below the graph.
You get to see high school students that are able to produce these models that, hopefully will eventually be implemented in solving these real life issues in the world.